Playing with Systems by Mark Rubin. When I was a kid, I used to play with marbles in my room. I set up a ramp and I would roll the marbles down the ramp from different heights. I noticed that the higher the starting point, the faster the marbles rolled. I thought this was very interesting and I wanted to understand it better. So I set up some dominoes at the end of the ramp and I would keep track of how many dominoes were knocked over based on rolling the marble from different heights. The relationship between the starting height of the marble, the speed of the marble over time, and the number of dominoes knocked over showed me how the system worked. And I figured out how to build models of the system in my imagination, and those models showed me what was happening. But I always had marbles all over the floor in my room. It was annoying to have to clean up the marbles every day after my experiments. So I started thinking about it and I thought, maybe there's a better way to do this. So I had an idea. I thought maybe I can build a machine to pick up the marbles. And if I could do that, then I wouldn't have to pick up the marbles myself. And the way the machine would work in theory was I would roll the marble down the ramp, and then somehow the machine would pick up a marble and put it back on top of the ramp. It occurred to me if this actually could work in real life, that I could potentially create a machine that went around forever, because it would constantly be putting marbles at the top of the ramp and they would constantly be rolling down to the bottom of the ramp. So I thought about this for a while and I thought, maybe it is possible. So I thought about it for a few weeks and I tried different models in my imagination and I came up with this one. The first reports of this design actually occurred in the 8th century. So people have been thinking about the concept of perpetual motion machines, or machines that can spin around forever, for a long, long time. And this was my best design. So I wanted to think about different ways to try to figure out if it was possible or not to make a machine that would spin around forever. The way to determine if it would spin around forever is to see if the left side of the machine weighed more than the right side of the machine. If it did, it would constantly be tipping in this direction and spinning in this direction. So how do you figure that out? After some consideration, I knew it was impossible to make a machine that would spin around forever, but I built it anyway because I was curious about it and I wanted to see how long it would spin before it stopped. And I'm going to describe how I figured out that it was impossible. In order to figure out if it's possible or impossible, we have to break down the system. And the way we'll break it down is we'll break the system down into 3 functions: energy, information, and rules. And these 3 functions can be used to describe any system. So the first thing I did was I imagined it in motion, and I've taken away the perimeter of the wheel. And if it did work, it would work something like this. And the system changes over time. And this is showing the position of the marbles as the machine is rotating around. And after you create a dynamic model of the system, the next step is to freeze it in time and take a snapshot of it. And this shows the position of all the curved ramps. There's actually 6 curved ramps in the system. The next step is to reorient the ramps around a vertical axis so that you can see the left side and the right side of each ramp as it relates to the center point. And this shows you the structure of the energy in one snapshot in time. The next step is you add the marbles back to the ramps and you take a look at where they are at that one snapshot in time. And you just measure them, and you measure the distance of each marble to the center axis at these 3 different locations: location A, location B, and location C. And that distance is showing you the rules in the system, and the rules have to do with the curvature of the ramps. And what you find out when you do this is that the distances of each marble at each sequence are symmetrical. So the left side is always equal to the right side because the distance from the left at each sequence in time is the same on the left side and the right side. And what that means is that the distances are always in balance. So if the distances are in balance and each marble has the same weight, then the amount of weight on each side is going to be the same from the left side to the right side. And what you can do is you can break it down into those 3 different areas, A, B, and C, and figure out that the weight of each marble on the left side is equal to the weight of each marble on the right side. And do it again for B, and do it again for C. And when you put them together, you've got A, B, and C, and the left side is equal to the right side. So the total weight along the left side is equal to the total weight on the right side. And that's the information. It tells you what's happening in the system. Since this wheel is symmetrical, you don't need to evaluate any more snapshots. So any starting snapshot at any sequence is symmetrical to every other one. Therefore, knowing the relationship between the energy, the information, and the rules in one snapshot is good enough to know that it's always in balance, and that's why it doesn't work. The energy, the information, the rules are always in balance at each sequence in time, and that's why it's a balanced system. It's not an overbalanced system, it's a balanced system. Perpetual motion is impossible, and in this case, the reason it's impossible is because the energy, information, and rules are in balance at every snapshot in time. I love to imagine how things work, and I love to break systems down into 3 functions: energy, information, and rules. And if you can do that, it gives you a much greater understanding of how things work.